Every single time you stream a video or shoot off an email or even just load a web page, you are relying on this hidden foundation that makes everything work. We're talking about the absolute bedrock of all networking, the unsung hero that turns these abstract digital ideas into real-world energy. Okay, let's just dive right in and explore the physical layer.
It seems like a simple question, right? But the answer is, well, it's pretty fascinating. We always talk about data and information just flying around the globe. But what is that really? I mean, it all starts with bits, those basic zeros and ones. But they can't just float. They can't swim across the ocean. They need a vehicle. And that is the central puzzle we're going to solve today. How do these abstract bits become actual physical signals that can cross a room or an entire planet? So to answer that, we have to start at the very, very bottom of the networking stack. We're going right down to the first floor at the foundation that every single other layer, every app, every protocol is built on top of. This is the digital foundation. And here it is, the physical layer, also known as layer 1 of the OSI model. Its job is singular, and it is absolutely crucial. It takes raw, unstructured bits, just a simple stream of zeros and ones, and it converts them into a signal that can be sent over a physical medium. You can think of it like a translator. It doesn't understand the words or sentences, it just knows how to turn the letters into sounds. It couldn't care less about IP addresses or usernames or what website you're visiting. Its only concern is the raw transmission itself. Okay, so what's really interesting here is how specific these responsibilities are. The physical layer defines the absolute nuts and bolts of networking. I mean, we're talking about the shape of the plastic connector in your Ethernet cable, the exact voltage that represents a 1 versus a 0 inside a copper wire, the precise frequency of a radio wave for your Wi-Fi. It even dictates the speed limit, the bitrate of the whole connection. It is the rulebook for all the hardware, and it's what ensures a device in Japan can physically understand a signal sent from a device in Brazil. All right, so if the physical layer is sending out signals, what are they traveling on? This brings us to the actual freeways of the internet. And there are really three main pathways our data can take: through wires as electricity, through glass as light, or through the air as radio waves. Let's break these down. First up, you've got your standard copper cables, like the Ethernet cable probably plugged into your computer right now. They use electrical signals, they're cheap, and they're super easy to work with. The downside, their signal gets weaker over distance, and they can pick up electrical noise. Then you have the champion of speed, fiber optics. This uses tiny pulses of light traveling through these impossibly thin strands of glass. It is incredibly fast, super reliable over massive distances, and, best of all, it's immune to electromagnetic interference. Its main drawback, it's expensive to actually lay down all that glass infrastructure. And finally, of course, there's wireless, Wi-Fi, Bluetooth, 5G. It uses radio waves, which gives us amazing convenience and mobility, but, anyone who's had their Wi-Fi drop during a storm or stutter when the microwave is on, its weakness, interference. And this visual just perfectly illustrates the difference in performance. Think of bandwidth as the number of lanes on the data freeway. So copper, it's a reliable road. It's good. Wireless is also good, but it's a shared road. Everyone in the area is trying to use the same lanes, which can cause some serious traffic jams. But then, just look at fiber optic. Its capacity is in a whole other league. It's not a road, it's a massive superhighway with a crazy number of lanes, allowing an incredible amount of data to travel at the speed of light. Okay, so we've got our freeways, but how do we get the cars, our bits, onto them in the first place? A 0 or a 1 is just a concept, right? It needs to be translated into a language the freeway understands, whether that's electricity or light or radio. So let's get into the language of signals. And really, this gets to the heart of it. A bit is just an idea sitting in your computer's memory. A signal, on the other hand, is a physical, measurable event happening in the real world. A change in voltage, a flash of light, a shift in a radio wave's frequency. The entire job of the physical layer is to bridge this gap between the clean, abstract digital world and the messy, noisy physical one. Now, the technical term for this whole translation process is modulation. It's how we impress our digital information onto a real-world analog carrier wave. So, for example, we could decide that plus 5 volts on a copper wire means 1, and minus 5 volts means 0. For fiber, it might be as simple as light on for a 1 and light off for a 0. Of course, it gets way more complex, with schemes like QAM that can change both the phase and amplitude of a wave to pack even more bits into a single signal. Now, working hand in hand with modulation is something called encoding. So if modulation creates the basic sound, you can think of encoding as providing the grammar rules to make sure the message is actually understood clearly. See, we don't just send raw bits, we group them up and we apply a rulebook. And this has evolved a ton over time. Early Ethernet used pretty simple schemes, but modern high-speed connections use really advanced ones like PAM4 to pack multiple bits into a single signal change, which is how we get those blazing fast speeds. So why all this complexity? Why not just send a simple on-off signal? Well, because the real world is noisy. Signals weaken over distance, that's called attenuation. Other electrical signals can interfere with our copper cables, that's crosstalk, and EMI from things like power cables or even fluorescent lights. These encoding schemes are specifically designed to fight this. They build in timing information so the receiver knows exactly when to check the signal, and they create signal patterns that are way less likely to be confused with random noise. It's absolutely essential for error-free communication. All right, we have the bits, we have the signals, we have the pathways. Now, how do we physically connect everything together? This is where we look at the network's blueprint, or what we call its physical topology. So historically, networks were laid out in a few different ways. You had things like a single bus line that everyone tapped into, a circular ring, or a really complex mesh where everything connects to everything else. But let's just cut through the history lesson. Today, the vast majority of our wired local networks, like in your office or in your home, they use a star topology. This just means every device connects to a central point, which is usually a network switch. And it's just so much more reliable. If one device's cable fails, it doesn't bring down the entire network, which was a huge problem with the old bus and ring designs. And finally, let's talk about the hardware. The most important piece of physical layer gear for you is the network interface card, or NIC, that's in your computer. That is the hardware that does all the heavy lifting of modulation and encoding we just talked about. Other simpler devices exist at this layer too. Repeaters just boost a weak signal to help it go farther. Hubs, which are pretty much obsolete now, were just simple connection points that would broadcast a signal to everybody. And media converters do exactly what their name says. They might translate a signal from fiber optic to copper, for instance. The key thing to remember is that these devices don't think, they just handle the physical signal. So, the next time you hit send or you click on a link, just take a second to think about the incredible physical journey your data is about to take. Those zeros and ones are being translated into a physical language, they're being encoded for reliability, and then sent out onto a freeway made of copper or glass or air. The physical layer is what makes the digital world a physical reality. So the real question to leave you with is this. On its journey to you, which freeway did the data for this explainer travel on? Was it a current, a beam of light, or a wave? Chances are it was all three.